Hey everyone, good afternoon. I hope you're not tired yet, and I'll try to give something that it's a little bit different than what we've seen in the past couple of days. We've seen mainly let's make a better design, specifically in terms of the geometry and geometrical topology, of course, better fit, better materials. But here I'm going to show a tool that we've developed in Sentient that is focusing more on the performance of the part. Once, of course, we made a good part that has good tolerances. How about its performance while it is in the field, it is in the service? How much is going to last? How long it's going to last? Is it going to work for like 2 days, 1 year, 10 years? And with that, I want to emphasize that again, as you can see here, we are working only on power bed fusion. And again, as we are talking about mechanical fatigue, we are mainly working on metallic alloys, not on plastic or ceramic applications. Before doing that, Sentient Science is a small company. I don't have an introduction slide for that one. It's a small company. We are about 40 people now. My name also, I don't think is up there actually. Sorry for that. Oh, actually it is. It's on there. Behrooz Jalalahmadi. I'm currently the VP of Additive Manufacturing for the company, and I've been with the company for 12 years now. So again, we are a software company for mechanical engineering applications. The software solutions that we are providing, we are branding them under the name of DigitalClone, which is representation of, we are making a digital clone of the microstructure of the part and basically how it's going to behave under the loading and how it's going to fail. We have a few software solutions in that family. Today I'm going to talk about DigitalClone for Additive Manufacturing, which again is designed for AM part made by power bed and again for metallic alloys. It's an ICME solution, of course. So for any of you that are familiar with the ICME solution that are working on mechanical performances, you should be very familiar with these modules that are included in your software. They are well accepted by anyone that's working in that industry. That first of all, we are talking about the process module, then we have the microstructure module, and then finally fatigue module. I have a couple of slides on each of them, of course, in the following coming slides, but in short, as you can see, it's a multi-scale model starting from the full level. In the first one, process module is basically working with the entire geometry of the part at the macro level and simulating the layer by layer build process in the chamber. Second one now focusing on a much smaller dimension, another scale, focusing at the grain level and see how the microstructure is basically forming. And then finally, using those information learned from the previous two ones, combining it with the load that is applied and the material properties to predict fatigue life for the part that is under the investigation. And then, of course, considering all of the randomness and stochastic features that are involved in that process. The first one, process module. Again, it is at the macro level. It is working with the entire geometry of the part. It is finite element based, and it is using inherent strength methodology to basically simulate the layer by layer build of the part, simulating the change in the state of the material, going from the solid powder to the liquid melt pool, and then of course back to the final solid part through the solidification. It needs, of course, similar to any other computational model, it needs quite significant input parameters that can be divided to a few categories. Of course, we need input parameter as a geometry, like STL file. Then we need the set of process parameters that are set on the machine, like laser power, laser speed. And then also we need material properties. And again, the list of the material properties that we are using are including both macro level properties and which are very typical, like a melt pool or elastic modulus that we are all familiar with them. And then also we are using some micro level, grain level material properties that might not be very familiar for a regular engineer, but then of course we help our users to identify them and of course input them and use them. And then once we do that simulation, of course, what is the output? The output, of course, would be the part that comes out of the machine, out of the belt chamber, what is the residual stress that is left in the part? What is the deflection that is left in the part? And of course, using those to make a better design, right? What we have been talking in the past couple of days, that of course, how to make the part to make sure that we are in the acceptable tolerances in terms of the geometry of the part. And then of course, not having too much residual stress in the part to not breaking it off before even sending it to the field. Then the second module, Microstructure Module. One output of the first module is the thermal history during the build process. So basically we have temperature gradients for each location, each time during the entire build process. And then of course we can use those information, those thermal information, along with, again, material properties to predict what is the microstructure at any location of that part. As you can see here, we all know, it is impossible to predict the microstructure for the entire part, right? Because with the current computational powers that we have, that model is going to run for a few centuries. So hopefully soon, I don't know, Intel, AMD come up with some much, much better CPUs to be able to do that one. But for now, instead of that one, we have to focus on a very small part of the part. So basically, users select that specific location, that hot spot, which of course, it is determined, dictated by the geometry, by the loading of the part. Where is the weak spot that I like to focus on that one, make my microstructure for there, and see how it's going to behave under the loading and how it's going to fail. Again, we are predicting the microstructure in 3D, and then of course we are making 2D, as you can see here in the movies here, along the belt direction, perpendicular to that one. Also, what you can see on the left-hand side, in our microstructure generator, we are also able to predict the porosity that happened in the microstructure, and actually predict the porosity creation for both reasons, not enough energy or too much energy. Basically, the porosity that happens because of lack of fusion, or it is happening, when you're applying too much energy because of, boiling and the keyhole effect. Of course, the very first question that comes into mind, what is the validation? So here I'm showing a couple of use cases to show validation, some level of validation basically for that specific module. As you can see here, I'm listing for two different materials, Inconel 718 and aluminum silicon alloy. Both of them very well-known metallic alloys used in power bed fusion across the world. The first one here on the top left corner, I want to show flexibility of our model to input parameters that are set by the user. So I'm showing the comparison of our prediction versus the experimental EBSD for the Inconel 718, and the people in that literature that did that experimental work, they use the same powder, but they use two different set of parameters on the machine, and as you can see, the microstructure significantly changed because of those different set of parameters. And in the lower row, you can see that basically I did the same thing, that if I use the same material property, but I changed my process parameters, as you can see, the microstructure that also we are predicting, it is behaving differently, very similar to what is seen under the, again, EBSD. On the right top hand side, I want to show you some quantitative values of the validation. So again, as you can see, the microstructure that we are predicting for a aluminum silicon alloy, as you can see, both qualitatively and also quantitatively on that normal distribution is very similar to what was seen, again, under EBSD. In the lower part, again, as I mentioned in the previous slide, I'm showing responsiveness of the model on predicting the porosity when I'm changing my process parameters. Of course, OEM is a machine OEM is providing a default optimum set of parameters that if you do that one, you get the best microstructure. But then what happens when we deviate from those for any reason? And again, you can see the comparison of our prediction in the lower right-hand side, the prediction of our model versus experimental build of those aluminum silicon alloy part, and how close, or in some cases not that close, comparing to those experimental porosities. Coming to the fatigue, and fatigue actually is the core value of our company. Sentient has been established about 22 years ago. And mainly, even before coming to additive manufacturing, it was about microstructure and its effect on the fatigue, and that's where the company has the strongest technology there. Our fatigue engine is even US patented for both, again, non-AM metallic alloys, and then also extending it to the additive manufacturing, especially power bed metallic alloys. As you can see here on the left-hand side, I'm showing one of the features of the software, which is providing the statistical analysis through the variable distribution to be able to investigate the statistical and the randomness of the data, and of course, getting L5, L10 values. And then also on the right-hand side, a very familiar curve for any mechanical engineer, beautiful old school SN curve. And the biggest value here, of course, is that if you want to create that SN curve experimentally, we are talking about a few months of work. And of course, $1 million of money, to spend on, making those samples and testing them. Fatigue testing is not cheap. And while computationally, of course, I can create that SN curve in a week. And of course, much cheaper than, you have to do it on the test rig. As I mentioned, we are using our fatigue engine. We are calling it CLP. It is component life prediction technology. It is, again, US patented. And why it is unique in a sense, it is because it is based on damage mechanic, fatigue damage mechanic. I'm not sure how many of you are familiar with that one, because most of the, fatigue software that are out there are either based on extensive empirical data that they do some form of interpolation and making decision out of those, or they are based on some standard like ISO standard with a lot of correcting factors based on your conditions. Or even if they are computationally, they are based on linear fracture mechanic. This is based on damage mechanic, and its biggest advantage compared to fracture mechanic is that you do not need an initial crack to start your simulation and see how that crack is going to basically get to the failure, which is against what you need in fracture mechanic, right? In fracture mechanic, you need initial crack, and then basically you're simulating how long it's going to take for that crack to become critical. What is missing in that is that when you assume that initial crack, you are overlooking your crack initiation stage. And most of our customers are in aerospace, and in aerospace, crack initiation stage is all they care about. So you cannot do that one with fracture mechanic, right? This one can predict the crack initiation stage, which, when you're talking about high cycle fatigue, could be all the way up to 90% of the entire life of the part. And that's the value right there. I'm showing a couple of use cases here. First one is on the simplest case that we can do on fatigue is just a simple dog bone under axial loading. The simplest case of fatigue testing that we can do. This one was made again by PowerBed for stainless steel 17-4. As you can see again, we did the prediction of the microstructure and then did the fatigue testing and also fatigue simulation. Excuse me. And what you have to notice on the right-hand side image is that the prediction that we are making compared to the real data is pretty wide. And the reason for that one is that basically purposefully when we are doing the simulation, we are considering the worst case scenario to the best case scenario. That basically, in terms of fatigue, what that means worst case scenario is when you have a bad flaw. You have a big inclusion, big void, and it happened that that bad flaw is also in a worst location that it could be, right under the load, right? And then in the best case scenario is that either you have a very clean microstructure or the void that you have is not in a critical location. So we are predicting that range to make sure that we consider all the possible scenarios. And then, of course, as you can see, experimental data are right in the middle of that behavior. However, if you go to a little bit more complex part, like this one, a single gear tooth, which is under gear tooth bending fatigue, now you can see that even the experimental data start to become wider because now we have more material, more possibility for the failure, so even the experimental data are wider than a simple dog bone. And again, this one was made from C64, which is a high strength aerospace grade steel. And again, we did the microstructure prediction, we did the fatigue testing, and you can see the comparison of our prediction versus the experimental data. Let's making it even more complex. This is a high pressure manifold, again from aerospace application. And in this manifold, the loading is not mechanical loading, it is through the dynamic pressure. So the pressure inside the manifold on the test rig, it was going to some predefined value and coming back to the zero. And that was the fatigue cycle in terms of the loading, the changing pressure inside the manifold. And again, same thing as you can see on the top there, on the right-hand side, the experimental EBST and our prediction of the microstructure. And then you can see the SN curve. And that's another value right there, that because the fatigue testing was expensive, the customer only did it for one specific load level, those red dots. And versus our simulation that, of course, we did that load level and also repeated it for 4 more load levels. Because again, coming back to the original point that I made, fatigue testing is expensive, it is time consuming. And let's making it more efficient, cheaper, wiser through the, of course, computational design and computational testing. In terms of timing, again, running the simulation similar to any other computational package depends heavily, on different parameters. How big is your model? How many simulation you want? How complex is the loading? How complex is your microstructure model? But to give you some, nominal values, you can see that the first module takes a couple of hours. The second module, we are talking about half a day. And then the last module, as we are running it, on HPC servers, we are talking about a few hours all the way to 24 hours again, based on the size of your model and the complexity of the model. This slide kind of summarizes different type of outputs that we are providing through those different modules. Again, all the way from deflection, residual stress coming right out of the machine, the microstructure coming out of the machine, fatigue test result computationally generated, of course, and then also in the bottom there, for if you are a mechanical engineer in the audience here, this is our porosity map that basically user can set a couple of input parameters and ask this simulation to provide a porosity map for them to show where they choose their process parameter would be the most beneficiary to produce the least porosity. This is our current material library. Whenever we are working with a new material or a new machine, of course, we are going through the calibration. That calibration has both experimental and computational part. We are doing it, with collaboration with our customer. And the way that we are doing the calibration, we are calibrating material/machine. As you can see here, those X marks are for a combination of material and machine. That means that right now, as you can see, for example, we have done the calibration of titanium 64 on a Reynolds machine, but if you want to do same titanium 64 on the EOS 290, we have to do calibration for that specific machine. So in summary, in the past few minutes, I tried to introduce you to one of our software solutions called DigitalClone for Additive Manufacturing, which is designed for mechanical application, focusing especially on the microstructure and mechanical performance, especially fatigue of the metallic components made by power bed, and producing different type of outputs out of each those modules. And again, it has been validated through extensive SPIR government-funded programs and also quite a few commercial projects that we have had, mainly in the aerospace industry. And the value, again, emphasizing on that one, that doing the qualification, doing the mechanical testing, it is cumbersome, it is time-consuming, it is expensive. Let's make that process, more efficient. To at the end of it, instead of spending $1 million on a couple of scenarios, of course, let's spend that $1 million on 100 different scenarios, and let's do the first few iterations computationally to see how many of those hundreds even worth, do the experimental exploration and validation, and of course, again, make the most out of your money. I'm going to finish with our brag slide. I'm not sure how many of you are familiar again with the NIST, National Institute of Standards and Technology here in the US. They are holding a competition for AM excellence every other year. We attended their competition last year, they had 26 topics. We attended in 6 of those topics based on the scope of the work that we do. And out of those 6 topics that we attended, as you can see here, we were awarded with 4 first places on prediction of the microstructure and residual stress and deflection behavior of Inconel 718 and Inconel 625. So by that, if you see something that might be interested to your work, I would love to talk to you more. Please come and find me later, in the break in our desk. Thank you very much.